So if you take any network conversation, the best way to see what it is and where it is, between whom it is, how it is, it's through debugs and using Wireshark. So if you understand that much, it's more than enough. How it is encrypted, what is happening inside, those stories are how, in what way it is going to benefit us. It's an algorithm. It's an
Oh yeah.
algorithm which you cannot do anything. You cannot alter it. If it is 256 algorithm, it will use 256 bits uh, to make a hash value. If it is 56 bit, then it is going to use only 56 bit to generate that encryption, encrypted key. See, it is taking your password, it encrypts, it creates a hash value, and for integrity, it adds a Diffie-Hellman algorithm value, and then they are going to exchange. Both the side they use the same algorithms to encrypt and hash and integrate, so they can understand each other. R1 can understand R2's key, R2 can understand R1's key, and they will evaluate whether the key is matching. If the key matches, phase 1 is done. This is what phase 1 tunnel. More than this, yeah, you can talk, but what is the use? First phase, key exchange, period, boom. They exchange the key, which no one can receive. Whatever R1 sends, only R2 can receive. Whatever R2 sends, R1 can receive, because we are not only sending the key encrypted, encapsulated, integrated, we also send it to a particular neighbor address. So if someone spoofs the neighbor address, the integrity will take care. So basically, the knowing of each other happens in phase 1. Knowing of each other, identifying each other. And for more security, they do rekeying every hour. They do rekeying every hour. You can change every 5 minutes, every 24 hours. That is phase 1. In phase 2, using the algorithm which we specify in the transform set, algorithms like 3DES, DES, AES, the data are going to be encrypted. And then using the hash algorithm that you give, it's an optional one. If you give, it's going to use that algorithm to hash the data and send, which adds more complex security, more security. More algorithms you use, more process is also utilized. You should understand that. And then the data is sent where no one in the middle can receive nor understand what is going inside the packet when they sniff. So phase 1 is key exchange, phase 2 is data exchange. This is what actually happens. Now what I'm going to do is I'm going to use the Wireshark. I already on the Wireshark. I'm going to provoke and make the VPN come up, and you will see phase 1, phase 2 packets. Phase 1 packets will use UDP 500 port number, which uses ISA-KMP protocol. ISA-KMP is nothing but key exchange. Phase 2 uses AES, and that's all you will see. AES is carrying your payload, your data. Now let's do that. Between R1 and R2, I'm going to ping. I want to keep the Wireshark at the background. I'm going to ping from R1 to R2. R1's IP address is 10.1.0.1. We are pinging 10.2.0.1. 10.1.0.1 to 10.2.0.1. Okay. Sure IP route. You got static route to reach this. This will be using the tunnel. Ping 01 using source. Your loopback. As soon as I hit enter, you will see at the background, not the ICMP packet. I repeat, usually when you ping, what do you used to see in the Wireshark? ICMP packet. But this time, it has been encrypted and encapsulated with ESP. So you will see a lot of ESP packets. Initially, you will see ISAKMP, which uses UDP 500. Boom, I hit enter. Finish. See all ISAKMP and ESP. That's all. Stop. That's all actually we need to know. But still, if someone talks for hours, they want to show
Sir, sorry.
how the encapsulation, encryption, how the bits, because he knows about those algorithms. He speaks, but what is the use?
So, sir, ESP the payload, right? The encrypted payload, the ESP. Is it
ESP,
right?
encapsulation security payload. ESP.
Okay.
Okay, you see here. Phase 1, I said it will use ISAKMP. That's the very first beginning. Router 1 is sending to router 3. The two tunnel endpoints are negotiating. Router 1 is saying, 500 UDP and payload. This is what we call it as key exchange thing begins. The key exchange thing begins. Internet Security Association Key Management Protocol. And then version 1, identity protection, main mode. There are two modes, main mode and aggressive mode. We'll talk about that later. Okay, so not encrypted, no commit. This is the very first packet, so no authenticator, no encrypted. It's actually a security association. See how big it is. It's too big. It's too big. A lot of things are going. If you use a lot of more algorithm, more complicated it will be. Identity only true. So it's just for key exchange. So it is taking the proposal. You remember we created a proposal. What is the proposal? Encryption, hashing, algorithm, that combinations. It takes to negotiate. See, we use 3 days. So R1 is saying, hey, this is what my encryption is going to be. This is what my hash is going to be. And Diffie-Hellman group 5 we said. That's why it shows this. And I'm using pre-shared key. Remember the password we gave? I'm using pre-shared key. So whatever we configured on router 1 is now negotiated with router 2.
So here, like encryption algorithm is for encrypting data, not encrypting the key, right?
No, encrypting the key. That's right. Encrypting the key, not the data.
Okay, okay.
And now here you see the time, the duration of the key is 1 full day, not 1 hour. It is 1 full day. 864,400 is 24 hours. All right, in seconds. Every 24 hours, the rekeying happens. So, like this, you can open and see what has been negotiated. Just I showed you the first packet. Likewise, here is the second packet. Second guy also says, yes, I also use the same combination. It's not saying I am also using. It says this is what I use. And now, actual negotiation starts. See, they send the password encrypted. Everything will be, it will send the hash, it will send the uh, encrypted key. See, the key exchange is what happens. This is the key hash value that is exchanged. See, dot, 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 which means there are many more things. More stronger the algorithm, more bigger the key is going to be. Actually, the password that we typed is very simple word. I think I gave something like spirit or something. Even the address, the port number to which it is sending, everything is encrypted. Yeah. So this XAT means extended authentication. Right. So when phase one is successful on either side, when it is successful on either side, then only they can bring the tunnel up. The tunnel comes up, and you see the algorithm that I used in phase two transform set is AH. That's why it is coming here, authentication header. Let me show you the command parallelly. If you go to R1, show run section crypto. You see, I said AH as the transform set and ESP AES. So for hashing, it uses AH, HMAC. Sorry, and then ESP, encapsulation security payload. So everything is encrypted. You will not see anything here because it's the data going inside. It won't show you anything here. No data will be sniffed. Not possible to sniff. And Wireshark, they're very strict. They show only what is necessary to be shown. They don't want to put any fingerprints on data. You will not see anything. Actually, it is ICMP packet. Only you and me know because we used ping as a command. So these are all ICMP packets. All right. So 1, 2, 3, 4, 5 pings we did. So five echo request and 5 echo reply. But one was not successful because it was trying to bring up phase one. So totally 8 packet you will see. To and fro. This is 1, this is 2, this is 3, and 4 should be down. This is 4. 4 ICMP packet, 4 response. Yes, question please.
Okay, for in phase one, basically, uh, we decide like what kind of encryption, what technique, and what kind of integration technique we're gonna use. And in phase two, basically we implement those techniques, right?
No, 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 no. Please understand, they are two different things. You are mixing both.
Yeah.
In phase one, we are encrypting with this algorithm only the password.
Okay.
In phase 2, we are encrypting our data with this algorithm.
Now got the idea. Yeah. Now I understand fully. Yeah.
Yeah. So there is no algorithm in phase 1 dealing with the data. No.
Okay. I got it. Okay, sir.
So you can have different combination for key and data. That's what I'm showing here. There is no connection. That encryption is only for data. Sorry, key. Phase 1 is for key. This encryption and hashing is only for data.
Data.
Now, because the phase 1 itself is very strong, there is no need to be a heavy algorithm here. But I have put a heavy, strong algorithm here. SHA is stronger than MD5. EES is stronger than DES. But usually, I have seen those people who have got a good security and quality sense, what they do is then they say, why to make more complicated, why to put big strong algorithm which is consuming more processor. So they put simple algorithms like DES. Sometimes they don't put this one HMAC. They want to only encrypt, they don't want to hash. So yeah, it is allowed, only encryption is allowed. So they put ASP DES instead of AES. But your wish. But make sure whatever you put on the left hand side, you also put it on the right hand side. Now, some verification commands which we have not done in the previous class. Show crypto map. This is the crypto map that we wrote. In this crypto map, we say you need to use phase 1 IP ISAKMP, phase 2 IPsec transform set. The peer to which you need to negotiate is 32.32.32.2. And the access list that you're supposed to use is 101, which is allowing only the traffic going from 10.101 to 10.2.0.0. So you see, the show crypto map shows everything in detail here. You don't need to go to access list and see what is 101. Right here itself, it shows what is 101. And then this is the peer, and then security association for 30 for how many hours? For this key association happens every 1 hour, I think. Yeah. See, key exchanges every 1 day, every 24 hours, the same key. But here, this is going to cross check whether it is same or not every 1 hour. And then for transforming the data, it uses ESP, AES, and for hashing, it uses SHA-HMAC. And it is applied on this interface G3 /. This is the tunnel source opening of the tunnel. End of the tunnel is wherever this peer is. So this is a nice command to troubleshoot. If it is not working, maybe we have made some mistake in access list. You just type show crypto map, it shows the entire story in one place. What is your transform set? The only thing it won't show is the phase 1. Because in the interface, it is the crypto map that is binded. Inside the crypto map, we have not shown the proposal of phase 1. We simply said go and check the ICMP profiles. We may have multiple ICMP policies, whichever suits. I repeat, we may have multiple ISAKMP policies, whichever is matching with router 2, that is what going to be used. So that cannot be displayed here. What we use is show run section crypto. We use just one policy. This is what is not shown in the show class map. Sorry, show crypto map. Other than these things, all the rest of the things are displayed here. Why? Because this phase one, you may have multiple policies, among which one policy will be matching with your router 2. So that cannot be shown in CryptoMap, that's why it's not showing. Show CryptoMap is one command. Secondly, in order to see whether the phase one is up or not, I used this command even in the previous class. You type show crypto ISAKMP SA means security association. I'm asking to show security association for phase one. I'm asking to show the security association of phase one. And it shows the destination with whom the security association is made is 32.32.32.2, which is the address of router 2, the public address. And then the tunnel source is 13.13.13.1, which is also public address. So the tunnel is only using the public address. That tunnel is used by the private traffic. And it is currently comfortable idle, means everything is set. And the status of the tunnel is active. This is a connection ID which is automatically generated. If you have another VPN, then it will be 1002. Second command is the most interesting command, which I always use. I love to use this to see show crypto IPsec SA. This is phase 2. Remember, even when we configured, we said ISAKMP for phase 1, IPsec for phase 2 transform set. So in order to see phase 2, just type IPsec. You don't need to worry about the command. You will know this because when you configure transform set, you used crypto IPsec command. Now this is the nice place where you see a lot of interesting stuff. You see that the VPN is using this physical interface, and this is the local IP address, the source IP address. And the VPN will be carrying the traffic of the customer inside traffic private 10.1, the user traffic 10.1 to 10.2 only. This is the address that need to match in order to use this tunnel. And for phase 1, it used UDP 500, means ISAKMP to negotiate, and it is granted, means this is successful tunnel. So for 4 packets have been encrypted and sent. Likewise, R2 sent with encryption, and this is decrypted 4 packets. So both sending and receiving is shown here. 4 packet encrypted while sending, and 4 packet decrypted because it was a reply packet from the other side. So you don't need to go to the other side and check. Now itself you can say that other side is working fine. Otherwise you will not get this 4 packet for decryption. The other side is encrypted. That's why you have the option of decrypting. So again, the local crypto endpoint is this, the remote crypto endpoint is this. These are the 2 places where the encryption and decryption happens, R1 and R2. Path empty is 1500. And if you go down, you will see the payload transform sets. Up, a little up. Yeah, here it is. ESP is one of the protocol that we use to encrypt. That is copied from crypto map called CMAP, which I mentioned that in order to transform your data, use ESP AES inside the tunnel. Right. So not only it says yes, it is supported and it is active. So not only this ESP for encryption, if you go down, you also had hash. So hash SHA-HMAC is also used. So the two algorithms for encryption. That's why if you keep it simple, only one, then it will be only this much, not this one added. Right. So you try to keep it simple. And then this is what called as tunnel mode. We are using tunnel mode. There is also something called transport mode. We'll see both the difference, tunnel mode and transport mode differences in a few minutes. So that's all phase 1 and phase 2 verification. Everything is good. So we are able to ping and get encrypted and decrypted successfully. Now, troubleshooting. What is troubleshooting? Troubleshooting is going and correcting the mistake someone has done. So how we will troubleshoot the site-to-site VPN? First thing, you will go and check whether phase 1 is matching. Before all this, you need to make sure the ping happens between R1 and R2, the public IP address. This 13, 13, 13, 1 to 32, 32, 32, 2, you should be able to reach. That is the very first thing that you should check. Because you are going to negotiate to this address. So first do the check. Secondly, configure go and check the phase 1. How do you check the phase 1? See, first is ping 32, 32, 32, 2. That pings. So there is a reachability, no problem. Negotiation can happen. Now, what are the things that are negotiated? That you compare. Show, run, section, try, say, KMP. Now compare this to with the router 2. So this is my way. If you want to troubleshoot comparing the Wireshark, you do, no problem. Or you will say, no. I am a CLI guy. I will not use Wireshark. Then either you use this way, which I am doing, or do debug. But debug will be like too many pages, a lot of lines, and you need to scratch your head a lot. That's up to you. What I do is I just go and see whether everything is proper. That's how I troubleshoot. More than debug, I feel this is more easy for me when I have access to both R1 and R2. I just see what's supposed to be there. If it is not there, I just go and correct it, and it will work always for me. You see, this number doesn't need to match. So here you can have 20 also, that's not a problem. This must match, it is matching. This is matching, this is matching, this is matching. The password should match. The address should be correct. The remote address 13, 13, 13, 1 is for router 2. For router 2, the remote address is 13, 13, 13, 1, which is router 1's address. Likewise, router 1's remote address should be 32, 32, 32, 2, which is router 2's address. I see phase 1 is good. There's nothing going to stop phase 1 coming up. Secondly, I'll check the transform set. Show crypto IPsec. here also I want to say that. And I just want to compare the algorithm. Both algorithms should be same. This name need not to be matching, not necessary to match. For hashing SHA HMAC, AH SHA. See, there is AH SHA, there is also EA, there is also another one. AH is authentication header, which is more good than, what is that? Another one, wait, let me, crypto, IPsec, some. There is also another weaker one, which is AH, okay, there is another stronger one, ESP SHA HMAC. We used AH SHA HMAC. There is also ESP SHA HMAC, which is more stronger. I do not want to use that. Anyway, what I need is the match between what is configured. It is matching. Here also I have AH SHA HMAC. Here also AH SHA HMAC. Here also ESP. ESP. See, this is what actually necessary to match, and VPN should work if you got the access list correct. Let's check the access list. Show run section access -list 101. And I would like to do the same on the other side. And now whatever here the source, it should be destination here. Whatever the source here, it should be destination there. Perfect. Hey, very nice. Matching. What is next? I'll compare the crypto map. Show run. Yeah. So make sure the peer address is same, and you have called the transform set and the access list proper. The access list is called, transform set is called, peer is correct. Next is apply this crypto map under the interface. This is applied under the interface. If you want to see, you can see show run interface G3/0. You'll see that crypto map called. That is all actually need to be good in order to have VPN. Even after doing this, if it is not happening, then the problem is at the routing. See, you wrote access list, those things are fine. But if you want to go to this destination, you need some route in the routing table, which is pointing towards this tunnel. Tunnel is where? Tunnel is binded to G3/0. So you need to have a static route saying in order to go to 10.2, go to this destination. You know why you are saying go to this destination? Only then it will use this tunnel physical interface. Tunnel is binded to this physical interface. Only when the traffic tries to go on that wire, the crypto map which you have binded will start working. So simply to push the traffic towards that direction, we write this static route. The static route is not really carrying the packet to the other end. No. It is trying to just use this interface so that the crypto on that interface will start tunneling by encapsulating with this as the source address and this as the destination address. If you see the Wireshark there, the packet, even though you're pinging from where to where, you're pinging from 10.1.0.1 to 10.2.0.1. That's what I was pinging. But if you see, the source is not 10.0.1.1. It is R1's public address to R2's public address. So in order to get that public address encryption, you need to push the traffic here. See, even though R3 do not know anything about 10 network and 10.1 and 10.2, you're able to ping it is all because of the tunnel encryption and encapsulation. Router 3 has got no idea about 10.1.0.1 and 10.2.0.1. But you are still able to ping. I showed this even in the previous class. You're able to ping because of the encryption and the encapsulation. Encapsulation is 13, 13, 13, 1 and 13, 32, 32, 32, 2. That's what you saw in the Wireshark. So using that source only, the packet is getting routed in the internet, not the original source. Original source is totally encrypted. You will not see the original source. You open and see. Do you see any original source 10 starting with 10.1, 10.2? Nothing, nowhere. It is totally encrypted. That is what called as tunnel mode. Tunnel mode is the original source and the destination is totally hidden. Transport mode, you see, if you go to transform set, you will see two modes. Let me show you. If you go inside the phase 2, I'm just going inside the phase 2 and put question mark. You see a command called mode. The default mode is tunnel mode, where your original source and destination is also a part of data, and it is encrypted. No one can see the original source and the original destination. Whereas transport mode is the tunnel interface G0/1, G3/0, no? That itself is a tunnel source. Please understand, I'm going to repeat. I'm trying to explain you two different modes. The default mode is tunnel mode. What does that mean? When you ping from here to here, the original address 10.1.0.1, 10.2.0.1, source and destination, and the data. In our example, it is ping, ICMP data. It can be FTP, it can be mails, whatever you send through the tunnel. That is the data. Now what happens is, in the tunnel mode, as it enters the tunnel, what is the tunnel source? 13, 13, 13, 1. Tunnel destination 32, 32, 32. That is what getting added. And then what ESP does is it encrypts all this portion. So right from original layer 3 to layer 7 is encrypted. This is what tunnel mode. This is what default mode. When you go and type this command show crypto ISAKMP SA, hey, funny router. Show crypto IPsec SA. When you see tunnel here, what does that mean? It means what I explained you now. It means that the original layer 3 header is also encrypted. That is tunnel mode. What is transport mode? Transport mode is your tunnel source is this in tunnel mode. Tunnel source and tunnel destination. Traffic source. Traffic source is this, tunnel source is this. Traffic source is this. In transport, when we will do transport mode, if the traffic source and the tunnel source is same, listen carefully. Any traffic that originates from this port going to this port need to be tunneled, if that is your idea. Anything, meaning both the tunnel and the traffic source is same. So you are not pinging from 10.1, you are pinging from 13, 13, 13, 1. And you are pinging to 32, 32, 32. So if this is your expectation, your expectation is whenever I ping from here to here, it need to be encrypted. It need to be IPsec VPN. In that case, you don't have a separate address as a tunnel address. You don't have a separate address as traffic source address. Both are same. Traffic source is also same. Tunnel source is also same. So what happens when you say transport mode? When you say transport mode, instead of adding an additional layer, in the tunnel mode, additional layer is needed because you have two separate source, two different source and destination. Two different source in the tunnel mode. Whereas transport mode, because the source of the traffic and source of the tunnel is same, because the source of the traffic and source of the tunnel is same, you don't need an additional header. So what you say is, you say the router, when it forms VPN, it should not encrypt this. Don't encrypt this. So no additional layer is added, no encryption is done, so that if you encrypt, what will happen? You cannot read and transport it. You cannot read and transport it. See how the name is given, transport mode. The header itself, the original source header itself will be used for transportation. Will not be encrypted. Only layer 4 and above, that is what you need to be very clear with. Only layer 4 and above will be encrypted. Layer 3 will be left. No new additional layer 3 will be added. The original layer 3 itself is going to be used for transportation, moving the packet. Alright, so that's the difference between tunnel mode and transport mode. Right. That's about site-to-site IPsec VPN. There's nothing much more than this needed.